Hey guys, here's some little practice problems. I just wanted to run through these to let you see if you think you're where you are with this as you close in for the test 2 here. All right. First one here says find the mass of a box with a weight of 20 newtons, and you of course remember that weight is equal to mass times gravity. The weight is how much gravity pulls on the stuff. The mass is how much stuff there is. They're related, but they're not the same thing. So if I know the weight and I want the mass, then I got to solve this thing here. So mass equals weight divided by g, and that would be 20 newtons divided by 9.8 meters per second squared, and that's about 2 kilograms there. I didn't pull up my calculator here, but you can imagine where this is going. 20 divided by 10 would be 2, so 20 divided by 9.8 is going to be a little bit bigger. How about 2.04, something like that. What happens with the units here? I got newtons on top. A newton is really a kilogram. Meter per second squared, I got meter per second squared on the bottom. These all cancel. I got kilograms. Okay. Number 2 here, what force is needed to stop a 1,500 kilogram car traveling at 30 meters per second within a distance of 100 meters. So right here, they're talking about force, and every time you see a problem with force, you need to draw a picture of the object and what forces are acting on it. Well, here it's going to be the brakes of the car. I guess you could have a parachute or something, but the car is moving this way, so I need to exert a force in the opposite direction. I need to overcome that velocity there with a negative acceleration, slow this thing down, bring it to a stop. Okay? Well, they don't tell us what that force is. They do tell me the mass of the car is 1,500 kilograms. They do tell me that at the beginning of the problem, the initial velocity is 30 meters per second, and over here I want that to stop. And I've got 100 meters for that to happen in. So looks like there's some kinematics going on right there. If I came through with one of my formulas of kinematics, then I could solve this thing for A and put the numbers in, and I would have the thing. Now v squared is 0. So I've really got here a negative 30 meters per second. That gets squared, and I'm dividing by 2, also dividing by 100 meters. And so my acceleration works out to negative 30 squared divided by 2, also divided by 100, would be negative 4.5 meter per second squared. That is not the force that they were asking for, but we know that every problem in this chapter somewhere is either going to use F equals ma or possibly the sum of the forces. This one only has one force, so it's okay to just leave it F equals ma. And we want that force. I got a 1,500 kilogram car. It's decelerating at negative 4.5 meter per second squared, and we can get a number pretty quick off of that. Just go right here, times 1,500 would be negative 6,750 newtons. The negative, of course, means to the left, backwards, opposite the direction of motion. So that's nice. Right here I got a 20 kilogram box sitting on a table. Let me go ahead and draw that much here because I need to see this. I need the picture of the object and all the forces on it. It says a person is pushing down on it. I'm going to put a downward arrow right here. Sometimes people like to draw that on top, and that's fine. But this is the person. I'm going to just call that P for person right there. And that's 10 newtons of force. Okay, so I need to think, are there other forces that are on this? We're looking for the normal force, and of course that's the force of the table pushing up. So that's this one right here. The other force, of course, is gravity. If I've got 20 kilograms, then I've got to add one more arrow here and put mg like that. So right here, those are all the forces. I've got gravity, I've got the person pushing, we've got the normal force on there, 3 forces, and when I sum those forces, it would look like this. I'd have the normal forces up, the other 2 are down, so I'll put opposite direction on it. The table is not, the block is not moving, the acceleration is 0, so we'll cross that out, and the normal force would simply be the weight plus how much ever the person's pushing down. The table has to push up to cancel out the weight. It also has to cancel out the person pushing up. And you can see where the numbers are going to go real quick with this. Like so. That's almost 200. This is 10, so we're real close to 210 here. If you want a little bit better number, then I would have this right there, 206. Okay? So there's that one. Right here, a force of 100 newtons acts on a 4 kilogram mass which sits on a frictionless level surface. If I had a frictionless level surface, that'd be like a table or a frozen lake or something. And right here I have a 4 kilogram mass, and the only force that I have is this person pushing on it. Doesn't really say which way it goes, but I'm going to draw it to the right here. It could be to the left or into the board or out of the board, whatever. But there's that right there. I've only got one force. There's no friction. There's no downhill pull. There's no string. This is all I've got. So I don't really need to write the sum of the forces. I can just write F equals ma here. And knowing the force and the mass, it's pretty easy to get the acceleration of this thing. This is very similar to that problem we did a moment ago where that's going to be 25 meters per second squared. Would be my acceleration. With that one we did the kinematics and then we did Newton's law. This one we got to do the other way. The big question is, what's the acceleration? Oh, I guess we're done. All right, never mind. I thought there was another question on that, like how far does it go? We're done. Next, number 5. A force of 100 newtons acts on a 4 kilogram mass which sits on a level surface with coefficient of friction of 0.7. Find the acceleration. This is the same problem that we just did, except now we have friction. So I come in here and I say I've got the 100 Newton force that we did before. And it's still the same mass, 4 kilograms. Only this time I do need to put in a frictional force pointing backwards. And I know that because right there mu equals 0.7. So this one has 2 forces on it. And the sum of the forces equals mass times acceleration. I got the force pushing it forward. I got friction backwards, negative, taking away from the speed. Anything that speeds it up needs to go into this as a positive term. Anything that slows it down like friction is going to be a negative term. There's equals ma, like that. Now I know that friction on a level surface is mu mg. So we could fill that in. I'm trying to get a by itself here, so if I divide through by m, then I'd have everything ready to go, and I could put my numbers into that, and that is going to be 100 newtons minus 0.7. The mass was 4. G is 9.8 meters per second squared. Should have put kilograms here, and I'm dividing by all of this by 4 kilograms, like that. So I'm going to pull up my calculator. We'll run through this one, make some room. I'm going to put parentheses around the numerator to make sure all that happens first. 0.7 times 4 times 9.8. Close that parenthesis up so the numerator's closed. I can divide the whole numerator by 4 there, and I get an 18.14. You'll remember we got 25 meters per second when we didn't have friction, and now we're down to 18 because the friction is slowing us down right there. All right. Every problem, just read it and see what's in there, what arrows you need. Right here, a force of 100 newtons acts uphill on a 4 kilogram mass which sits on a surface. Coefficient of friction 0.7, inclined at 23 degrees. Find the acceleration. Same problem again, except now this thing is tilted up like that. Now, I put over here on the side this little list of possible forces, and maybe you want to put that on your note card before you take the test. every problem, we kind of need to say, is gravity an important factor in this? Gravity certainly pulls straight down here, but the normal force is pushing that way, and part of the normal force is going to cancel out gravity. So I'm going to forget about these two, and typically that works fine. If somebody's pushing up or down, then you need to go through and do that thing where you find the normal force, like we did, I think, in problem 1, but otherwise not. Do I have a downhill pull? Absolutely. Anything on a ramp, I need to point an arrow downhill and label it DHP. And we know that the downhill pull is always mg sine theta, so we'll have something to put into that. So we took care of the 23 degrees. Let me go ahead and put that down here too. Theta equals 23 degrees. I've got a coefficient of friction, so when I go through my list and say, do I have friction, the answer would obviously be yes. This box is moving uphill, so my friction is going to fight that. Will be backwards, negative direction. The friction is always backwards. I don't know if I can get a little arrow in there or not. Make a big arrow. Ah, come here. Irritating thing. Oh, I lost my pencil. That's the problem. All right, so there is the friction right there. And of course, I've got the 100 newtons pulling uphill. All right. So this is a lot like the last one that had the force and the friction, except now I've also got a downhill pull, and I got to put that in there. So you're just going through this list over here and making sure you get everything. Is there a tension? Any string? I don't see any string. Anybody pulling on it? Yeah, actually, that 100 newtons is supplied by somebody outside of the problem. So I've got those 3 forces resulting in 3 arrows, and I want to sum those 3 forces, and that would be 100 minus the downhill pull minus the force of friction equals mass times acceleration. 1, 2, 3 forces, uphill, downhill, downhill, positive, negative, negative. Easy as pie. All right, 100. This is always mg sine theta. The friction on an incline, and so long as nobody's pushing up or down, would be mu mg cosine theta. And that's equal to ma. Can't quite cancel out the mass here because I don't have m in this term. All right, so that kind of stinks. But I'm looking for a way over here. So I can divide through by m to save a little bit of space, and I'm lazy. Let me just cross it out on the right. I'm going to divide both sides by m. It canceled over there, came over here. All right, and we can put those numbers in. 100. The mass is 4 kilograms. Here's 9.8. I'm being super lazy with my units here, but I'm just trying to get these problems done for you. 23 minus 0.7 times 4 times 9.8 times the cosine of 23 degrees. Divide that whole mess there by 4. That equals A. Again, when you put this in your calculator, make sure that all of this happens before the 4, before you divide by that 4. I can't even see it all. There it is. Okay, so I'm going to put that opening parenthesis 100 minus 4 times 9.8 sine 23. Close up the sign, please. Also subtract 0.7 times 4 times 9.8 cosine 23. I need to close up the cosine, close up the numerator, and then divide by 4. And that would be a 14.9 meters per second squared. 14.9 meters per second squared would be the acceleration. We had 25 when there was no friction. We had 18 something when there was friction. And now you tilt it up, it's going to slow it down a little bit more because you got to overcome the downhill pull and the force of friction. All right, right here, find the force necessary to accelerate the set of blocks at 3 meters per second squared. A little picture at the bottom, so this is pretty straightforward. But what we need to do is to think about each one of these. This is the first one we've seen today that has 2 blocks. There's a block, there's a block. I need to know what forces are acting on this one. I need to know what forces are acting here. So 2 separate blocks. And says that mass 1, that's this back one today, is 9 kilograms. Mass 2 is 3 kilograms. And there's a coefficient of friction, mu 0.5. I'm going to write that down to remind myself to get the friction in there this time. Here's the little list. I need to run through the list for both boxes. Why don't we do mass 2 first? Gravity and normal force. Gravity pulls straight down, the table pushes straight up, canceling out these two. I don't need to worry about that for either box. It's the same situation. Is there a downhill pull? No, because it's not on an incline. Is there friction? Absolutely, because they gave me a coefficient of friction. So right here I need to come in and say this is the force of friction acting backward on M2. So I'm going to put a little blue check mark right there. Is there a string? Yeah, I've got two strings, or maybe one's a string and the other is another force. I don't know. But right here, this string pulls backward on that guy. I don't know why I jammed this in here so tight like that. And then I've got this force pulling forward right there, and that's actually what we're looking for on that. Okay, so 1, 2, 3 forces on that. I had a friction, I had a tension. That string pulling it forward is either a tension or another. I'm not sure. Let's call it another, like that. But I'm going to go ahead and build an equation for that box. Sum of the forces on mass 2, the front box, is mass 2 times A, and I see that there's an F minus an F sub F, the friction, also minus tension, and that equals M2A. One more time, if I reach in here with my scissors and cut this string, then mass 2 is going to move a whole lot faster because it doesn't have to drag mass 1 along. So that tension is a backward force on that. All right, let's put in what we know here. I certainly don't know F because that's what I'm trying to find. The force of friction would be mu M2G. Right here's the tension. I don't know that either. Here's M2A. The numbers that I do know, not that one. 0.5 is my coefficient of friction. I got 3 kilograms, 9.8 meters per second squared. I don't know the tension. The mass is 3, and they gave me the acceleration right there, 3 meters per second squared. All right. So what I think I would do is try to clean this up as much as possible. I'm really tempted to go ahead and get a number for this and add that to both sides. Get all those numbers together just to clean it up best I can. So right here's a negative 0.5 times 3 times 9.8. And that's a negative 14.7. I'm going to add that 14.7 to both sides. So 3 times 3 plus the 14.7 from the left-hand side would be 23.7. I could write F minus T equals 23.7. And that's as far as I'm going because there's two unknowns. I can't solve that right off the bat. So I got to do something else, which would be go look at the other block. All right, the block in the back, M1, is moving forward. Both of these blocks are moving to the right, like that. So see how we called F positive, and force of friction negative, and T tension, that conforms with our direction of motion, getting that right. When I do mass 1, I've got to use that same coordinate system. So it's moving forward not because of the force. The force isn't touching mass 1. The force is on mass 2, and then the string transmits some of that to mass 1. So it's that string pulling right there that's important. I do have a tension. It's that one. But I don't have an other because it's not, the force is on mass 2, not mass 1. All right. Do I have friction? Yeah, I do have friction with that coefficient of friction pulling back right there. So this would be F sub F, like that. What about the downhill pull? Nope, no downhill pull. The gravity and the normal force are going to cancel each other out again, so I don't need to worry about that. Just these two forces this time. And I would write the sum of the forces on mass 1 equal mass 1 times A. That's going to be T minus F sub F. That's equal to mass 1 times A. The tension I don't know. The force of friction is going to be mu M1G on a flat surface. That's equal to M1A. So let's see what happens here. I do know the coefficient of friction. I do know mass 1. I do know G and mass 1 and A. The only thing I don't know is T. So what we're going to do here is go ahead and put in all the numbers, find T, and then we can take that and plug it in right here. And that'll give us the force over there. That's where we're going with this thing. So let me go ahead and add mu mg to both sides. Here's m1. That should have had a little 1 right there. But on the calculator, we're going to take the coefficient of friction, which I already forgot was 0.5. And then we want to multiply that by mass 2. Mass 2 is 3 kilograms. And that times 9.8. And then plus mass... Oh, you know what? I really wanted mass 1, didn't I? These are labeled kind of backwards. All right. So mass 1 is 9. Let me try that one more time. Step over here. Instead of a mass of 3, it's a mass of 9. All right. Now I think we're okay. You see how nice the picture is, though? I didn't do it in the picture, and I goofed it up almost. Here's plus 9, and the acceleration was, what was it, 3, wasn't it? Yeah. Need all those numbers ready to go for you. I got a 71 newtons on that tension, okay? And I don't really want that. Well, actually, I do want that. What are we looking for here? Find the force. All right, so that is one thing. They said find the tension. We just did that. And now I'm going to plug it in over here, and we'll go back to blue here. And we'll have, thought we would. If I add that tension to both sides, yeah, then I would have F equals T plus 23.7, and that T, of course, is 71, and I add 23.7, and I'd get a 94.7 newtons right there. All right. Whew. Here we have one of these. There's a block on the table, and there's a block that's hanging. The string runs over a pulley. I've got my list over here again. We run through the list. I'm set up in blue, so we'll do the block 1 here in blue, I guess. Notice that it's going to move to the right. It's kind of good to figure out your directions before you get too far into this thing. This block is going to move to the right, and this block is going to move down. And that locks in our coordinate system. Both blocks need to move in the positive direction. When I think about the these forces for mass 1, the gravity and the normal force are going to cancel each other out. Gravity pulls down, normal force pushes up, same thing. I don't need to worry about it. I don't need a downhill pull because it's on a flat surface. Do I have friction? Yes, I do, right there. Coefficient of friction is 0.5. So let's put in an arrow for the coefficient of friction. F sub F. I got that one. Check. Do I have a string? Absolutely. I put it in T right there. Anybody reaching into the problem and pulling? No. Okay. So we're done. All right. For mass 1, that's what we need. And we'd write the sum of the force on mass 1 equal mass 1 times A. That'd be T minus F sub F equals M1A. I don't know T. I do know that the friction is going to be mu M1G, and that's equal to M1A. And here comes some numbers. T minus coefficient of friction was 0.5. Mass 1 is 4 kilograms. G is 9.8 meters per second squared. And that's equal to 4 kilograms times A, which I don't know. Cook all this down, you'd have half of 4 would be 2. 2 times 9.8 is 19.6. Make it just as simple as you can. That's the equation that governs how mass 1 is going to move, or at least accelerate. Over here, we need to do a similar thing on mass 2. So I start over with my list. And I say, does gravity play an important part of this? And here it's absolutely important. I don't have a table canceling out that gravity, so I do have to put it here. Need the gravity. There's no normal force because there's no table underneath there. There's not a slope or an inclined plane. It's not touching anything, so there's no friction. I do have a tension, though. The string pulls up. It keeps that block from free falling. So it would look like that. Sum of the forces equals, this is mass 2 here that we're talking about, mass 2 times A. Remember, down is positive, up is negative. The direction of motion is positive. And it would look like that. And we have some of these numbers. Mass 2 is 7. 7 times 9.8 minus T equals 7A. There's 63 and 5.6, 68 point, what did I say? 7 times 8 is 56, 68.6 I think, minus T equals 7A. I need to stack up those two equations and add straight down. Notice here that the T here, positive T, this is a negative T. Those T should always cancel out in all of these problems that we do. That's your safety check to make sure you got your coordinate system set up. If they don't cancel out, you set the coordinate system up. I'm going to step away from this one. I think you can stack those up and see where that one's going real quick. All right, find the tension here and assume that M1 moves uphill. Let's go ahead and mark our directions of motion. It says M1 moves uphill. So that's my coordinate system there. M2 is going to drop. Positive is down for that guy. I need to go think about the forces that are on it. If you want to run through the list over here, that's fine. For mass 1 on the ramp, the gravity and the normal force are going to get taken care of. All of the motion is parallel to the ramp, so I'm really just looking for forces that run parallel to the ramp. And that's going to be the string pulling it uphill, the downhill pull, and I do have friction here, so I need that one. All right. I do have a downhill pull. I do have friction. I do have tension. Nobody's yanking on it, so that's what I got right there. And right here I'd come in and say the sum of the forces equals mass times acceleration. This is block 1. So I'd have T minus DHP minus F sub F equals M1A. And, of course, the downhill pull is mg sine theta. And the friction is mu m1g cosine theta. And that's equal to m1a. All right, good enough there. How about the other block? When I do the mass 2, gravity is pretty important here because it's pulling down. And that's what's driving this whole thing. So m2g, let's make sure we get that one in. It's not touching anything. There's no ramp. It's not touching anything. The tension is up, slowing it down, opposite the direction of motion. So the sum of the forces on mass 2 equal mass 2 times A, m2g minus t equals m2a, and you can put the numbers in, stack them up, safety check, do my t's cancel. I got a positive t here and a negative t up there. So the t's are going to cancel when I stack those things up and add. Looks good to me. How about we do the next one here? Number 10, a net force of 3 newtons acts for 25 seconds on a 5 kilogram object which is initially at rest. How fast will it be moving? All right, fine. A net force means that they've kind of already added up all the forces, or maybe there's only one force, but the total force of this thing, the only force I need to worry about is that 3 newtons. Okay? They tell me 25 seconds. So, oops, looks like we're slipping back into kinematics here. I got some force stuff, so I got to do Newton's law, but time initially at rest, it's got V naught equals 0 twice in there. That's okay. See how there's a little bit of kinematics, a little bit of dynamics. So we're going to do both of those here. The mass is 5 kilograms. Wherever you want to put all, let's put all the kinematic stuff over here. V naught equals 0. How fast will it be moving? That's the final velocity. The time was 25 seconds, and that's only 3 numbers. So I really need 4 to do any kind of kinematics on it. Let's see what happens here. I got F, I got M. I know that somewhere in here I'm going to have to write down Newton's law. So it looks like that. I've got the force, I've got the mass. Ha! I could find the acceleration and then use it over here. Right? So F over m is going to be my acceleration. That's 3 newtons divided by 5 kilograms would be 0.6 meters per second squared. And now I've got that number. And I can whip up on this thing with some kinematics. I'm looking for a formula that has those 4 in it, and of course V equals V naught plus AT. Would do that really nicely. And I'll let you turn the crank on that one. It's already solved, you know, for the right form. Just put in 0. Gee, we could almost do this in our head. Here's a 0.6 times 25. That would be 12 and 3, 15, I think, meters per second, something like that. All right, so that's that one. Right here, I've got one of these. I don't think we've done one of these today. Again, I've got 2 boxes. There's a string and pulley. Find the time to drop 4 meters. Some more kinematics, but we got to do the Forster stuff first. All right, so looking for forces that are important here. M1, gravity does pull down. Looking at my list over there. Normal force, no. Downhill pull, no. Friction, no. Tension, yes. Okay, but nobody's pulling on it. All right, so that's the first one there. Because this block is moving up, then T is in the positive direction, M1G is in the negative direction, and I would get some of the forces on mass 1 equal mass 1 times AT minus M1G equals M1A. All right, over here, run the forces on this guy. What's a nice color? There's one. Okay, does gravity play a part? Absolutely. That would be M2G, and then right here's T. That way, I need gravity. It doesn't touch the table, so there's no normal force, there's no slope. It's not touching anything, so there's no friction, but there is a tension. Nobody's pulling on it, right? I got the 2. I'd come in here, sum of the forces on mass 2 equal mass 2 times A, and that's a T and an M2G, and that's equal to M2A, like that. This block is going down. I need to either let both blocks move in the positive direction. This one's moving up, so positive is up. This one is moving down, so positive is down. Or I need to have one coordinate system where it goes, my single coordinate system goes up, 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 bends with the string, follows the string, and comes back down on the other side. So right here, I really need to call tension negative and the gravity positive, like that. Again, safety check. I got a positive T here and a negative T there. The T's are going to cancel out. It's all going to be good. All right? You can finish that one up, I think. But, oh, there is one more. How about that? Right here, 5 kilogram mass sits on a ramp inclined at 23 degrees. All right? Box on a ramp. 5 kilograms, 23 degrees. Coefficient of friction. There's a string over a pulley to a hanging mass. All right, let's see if we can't set this one up. We'd like to find the second mass. This one sometimes people have trouble with. There's a little funny algebra thing you have to do here, but it's not bad. We're going to build the equation just like we always do. Where's that nice red? I thought we had that's kind of a burnt red, burnt sienna. The string is pulling uphill. The downhill pull and the friction are working that way. And that's everything. All right, gravity, normal force take care of each other. Do have this, this, and this. Nobody's pulling. All right, so when I write this thing up, I get T minus DHP minus F sub F equals M, what was that mass? I didn't name it, did I? Let's call this one M2, I guess. M2 times A. Okay, so I don't know what T is. This is going to be mg sine theta. So I'm going to go ahead and put 5 times 9.8 times the sine of 23 degrees. And the force of friction on a slope is going to be mu mg cosine theta. So that's going to be 0.6 times 5 times 9.8 times the cosine of 23 degrees. There's my friction. And over here the mass again is 5 kilograms. And they give me an acceleration 2 meters per second squared. All right, actually the funny algebra thing's not going to happen here. Here's a whole bunch of numbers. I want to get a single number out of that. And the easiest way to mess this thing up is to forget that little negative sign right here. Please start typing buttons and get a value for all of that, including this negative sign right there. This one's negative, this one's negative. They have to both point downhill, and it's really easy to start with a 5. You really need the negative in there too. So negative 5 times 9.8 sine 23 close minus. See how that one's negative and this other one's negative? 0.6 times 5 times 9.8 cosine 23, and that's a negative 46.2. So we'll put that in, negative 46.2. I got 5 times 2 on the other side, so that's 10. The tension is going to be 56.2 newtons right there, and the funny algebra thing doesn't happen here, so it's not that funny anyway. Nobody's laughing. Here is M2. Gravity is going to pull this guy down, so I need an M2G. The tension's pulling up, and remember this block is sinking. It's going down, so down is positive. This has got to be positive. This has got to be negative. And I'd get M2G minus T equals M2A. We're looking, the funny algebra thing does happen, I'm sorry. All right, so I don't know this number right there, and it's in 2 places. I do know the tension. I just found that. So why don't we add T to both sides and subtract M2A from both sides. I'm going to switch both of those at the same time here. Subtract M2A, bring that one over to the left-hand side by subtracting it from both sides. And then I want to take this guy over to the right by adding it to both sides. So it's going to be positive. There's that M2 right there. Here it is right here. I can factor that out front, and then I'd have G minus A. There's the funny algebra thing that I was talking about. So I'd get M2 equals T divided by G minus A, and the tension was 56.2 newtons. G is 9.8 meter per second squared, and the acceleration of this thing is 2 meter per second squared. So I need to come through here and say 56.2 divided by 9 minus 2 would be 7.8. Like that. 7.2 is the amount of mass. That's in kilograms. Newton is a kilogram. Meter per second squared. Cancel out the meter per second squared. You'd have kilograms. We were looking for a mass. That feels pretty good. Mass 2. I got to put 7.2 kilograms right here in order to pull this thing uphill, to overcome the downhill pull, overcome friction, and to get an acceleration of 2 meters per second squared. So that's what we did there. One more. I can't count. Will 100 newtons move a 40 kilogram box on a level surface? I got a coefficient of friction. Got 2 coefficients of friction. Mu sub s is static, so this one is not moving. And then on the mu sub k would be moving. If the box is not moving, if it's stationary, static, use 0.5. Once you get it moving, it's easier to keep it moving. So you kind of got to look at this thing and see what's going to happen here. I put 100 newtons on this box. It's 40 kilograms. And here's the table. Coefficient of friction before I get it moving is 0.5. So that means I need to draw in a frictional arrow this way. And when I sum the forces, then I've got those 2 arrows. I've got the 100 newtons to the right, and then I've got minus mu mg, the friction to the left, and that's equal to ma. And let's just see what happens here. 100 minus 0.5, the mass was 40, g is 9.8, and that's equal to mass, but the mass is 40 right there. And so we're really kind of saying, what is A? I could divide through by that 40. Let's do that real quick and see what we get. I got on the left-hand side 100 minus 0.5 times 40 times 9.8. All right, and the whole left-hand side is negative 96, and then I divide by 40, and I get a negative 2.4. Remember, negative points opposite direction? 2.4, is that what I said? Yeah. Okay. That suggests that when I pull to the right, the box accelerates to the left. And of course, that doesn't make any sense. Okay. The reason this doesn't work is because the friction is stronger than how hard I'm pulling. So it doesn't move at all. Right? It's not that it accelerates this way. If you get a negative number on this thing, it really means it's not accelerating, that the friction is winning, and that the thing is just stuck there. So the second part of this question says, well, if it doesn't move, then how much force would it take? We found out that 100 newtons is not enough, so I need to go figure out what it would take to move this thing. Probably the easiest way to do this would be to just go ahead and calculate the maximum value of friction, and then I've got to pull at least that hard here. So if I just go mu mg on this thing, before it starts moving, I've got a 0.5. Here's a 40 kilograms. The g is 9.8 meter per second squared. Now let's see what that number is right there. 0.5 times 40 times 9.8 is 196 newtons. Okay, my friction can fight me all the way up to 196 newtons, so clearly 100 newtons is not going to do the job here. I need to overcome that. The force to move it would be equal to 196 newtons. Okay, now as soon as I put 196 newtons on it and it starts to move, the friction changes, because then I got to switch over here and start using the other coefficient of friction. So now my acceleration is going to change. I've broken this thing loose. It's moving. I really got to do this one more time and say, great. And I guess the assumption would, you know, the problem didn't really say this because we've gone beyond the end of this thing, but keep pulling 196 newtons. And what would happen if I do that? So my problem now looks something like this. I'm pulling 196 newtons to the right, because that's how hard it took me, how much I had to pull to get it going. But now my friction is not 0.5 times 40 times 9.8. It's 0.3 times 40 times 9.8. And that's going to be a different number, and I need to know what that number is. Uh, 117.6. I think 118 would be okay. So when I look at this one, the sum of the forces equals mass times acceleration. We're always coming back to Newton's law. I got 196 minus 118. That was a 40 kilogram box times A. So if I take 196 and subtract the 118, put in some parentheses to make sure all that subtraction happens before I divide by 40, my acceleration is 1.95. If I keep pulling as hard as it took to get the thing moving in the first place. All right, and yeah, that's the last one finally. All right, that took a little longer than I wanted, but hopefully that'll make some sense. You can jump back and forth to these problems with the table of contents if you need. And thank you for your time. Have a good day.